Sequences in series, geometric sequences. So here we have type 5 where we're going to find an unknown using simultaneous equations. So in this example we have a geometric sequence, so we would underline geometric, and we're told that the third term is equal to minus 63 and the fourth term is equal to 189. So using this information we're going to find the first term a and or the common ratio. We're going to find the general term and then we're going to find the sum to n terms. Okay, so let's look at what we're given. So we know that T3 is equal to minus 63. So from that means that in general we would say our general term for geometric is given by T of n is equal to a times or to the power of n minus 1 from page 22 in our maths tables. So therefore that means that in this case n is 3 and our general term then is equal to minus 63. So we would say a times or to the power of n, which is 3 minus 1, and that's equal to the term minus 63. So in other words, a or squared is equal to minus 63, which we'll call equation 1. And then if we look at T4 is equal to 189, then we're saying n is equal to 4. And if I do the same again, we'd have a or to the power of 4 minus 1 is equal to 189. So therefore a or cubed equals 189. So we can't subtract these because we have a multiplied by or squared and a multiplied by a or cubed. So instead what we're going to do is we're going to divide the bigger one by the smaller one. So in other words, we're going to divide 2 by 1. So we would have a or cubed divided by a or squared is equal to 189 divided by minus 63. And the reason we do this is because we can see a goes into a once, and or squared goes into or cubed or times, and 189 divided by minus 63 is minus 3. So it's a nice quick way of finding our value for or. The other way in which you can do it is take a and say a is equal to minus 63 over or squared in equation 1, and then replace a with minus 63 over or squared in 2, and you would end up with the same thing. So it's the same thing as dividing 2 by 1. So once we know what a is, we can then what we know or is, we can then take or and sub or into equation 1. And if we sub or into equation 1, we have a times or squared equals minus 63. So that's 9a equals minus 63, and therefore a is equal to minus 7. So now we have the first term and we have or. We've done part 1. So part 2 is now to write down the general term. Where our general term is a times or to the power of n minus 1. So subbing in what we've just found, well, we know that a is equal to minus 7 and or is minus 3, and that's to the power of n minus 1. So again, I cannot simplify that any further because we would need to know what the power was first before I could multiply out any brackets. And the third part then just says, find the sum to n terms. Well, because it's geometric, and we know or is a number greater than 1, in other words, it's not a fraction, then we're going to use or to the power of n minus 1 over or minus 1. And therefore, if I sub in my values, well, we know again a is minus 7, and then that's minus 3 to the power of n minus 1 over minus 3 minus 1. In other words, we have 7 over 4 times minus 3 to the power of n minus 1. So on the worksheet that's titled Geometric Series, you're going to do question 11. And then on page 217 in your books, I get you to do 7. Okay, so type 6 then is word problems. So if we go to page 217 in your books, we're going to do question 18 as our example. So here we have estimates are produced for the number of babies born worldwide each year. The estimates for 2009 and 2013 are given in thousands of births to the nearest thousand, where 130,350 and 137,804 respectively. So we're told to assume that the yearly estimates are geometric progression. And the first thing it says is to find the annual percentage increase in the number of births, giving our answer correct to 1 decimal place. Okay, so what information do we know? Well, we know the births per year. So if we start with the year 2009, that's going to be equal to our first term, in other words, A. And the number of births per year was 130,350. The next thing we're told is 2013. So that's going to be, it should be term 5. Because if we look here, we have 2009, term 1, 2010, term 2, 2011, term 3, 2012, term 4, 2013, term 5. Okay, so if ever you're not sure, always do it out. And we know that that's going to be 137,804. So what we're looking for here is we're looking for the common ratio. What is that percentage increase every year? So therefore we know that the general term for our geometric is a times r to the power of n minus 1. Again from page 22 in our maths tables. Making sure we always underline geometric. So if I sub in my values there, A I know is 130,350. Or is what I'm looking for. And that's going to be r to the power of n minus 1. Well, if I'm looking at my fifth term, that means that n is 5. So that's going to be 5 minus 1. And that fifth term we see is 137,804. So in other words, that's going to be r to the power of 4 is equal to 137,804 divided by 130,350. And then if I get the fourth root of both sides, well then that's going to be approximately 1.014. And of course, correct to 1 decimal place. Well, or is what it's increasing by. So my percentage increase will be that 0.014 decimal. And as a percentage, that would be 1.4. In other words, that's representing the original amount plus that percentage increase. So this is the increases that we're looking for. So in part 2, we're looking to find the estimates for 2011 and 2016 to the nearest thousand. So if we're looking for 2011, well, if I go back to the start here, we can see that that is going to be term 3. And 2016 then, if we were to continue on, would be 14, 15 and 16. So that would be term 6, term 7 and term 8. So we're looking for term 3 here now and term 8. So if we're looking for term 3, We know that A is 130,350 times OR, we've just found out, is 1.014, and that's going to be to the power of n, which would be 3 minus 1. So in other words, if we put into our calculators 130,350 multiplied by 1.014 squared, and that gives us 134,025. So no decimal in our answer, just says nearest thousand. And then if we're looking for 2016, we said that that was term 8. So then term 8, well, A is 130,350 times or 1.014 to the power of 8 minus 1. So that's 130,350 times 1.014 to the power of 7. And again, no decimal, just to the nearest 1,000 would be 143,674. Now, in the back of your book, this is your answer, but realistically, the nearest 1,000 is what they've asked for. So therefore, we should be saying that it's 134,000. And for term 8, we would be saying 144,000, because the number that precedes 143,000 there is 6. So therefore, we'd round up. So they would be your nearest 1,000. Okay, so for part 3, then it says find the estimated total number of births between 2009 and 2017 inclusive. So therefore, what we're looking for is the sum of the births. So if we're looking at 2009 to 2017, how many terms is that? So therefore, the total number of terms if we go back, we can see is going to be one more year, so it would be term 9. So therefore, we'd have a total of 9 terms. So in other words, what we're doing is we're getting the sum to 9 terms here, where A, we said, is 130,350, or we've said is 1.014, and N we're looking for is 9. So therefore, the sum to N terms, again, if we go back here on page 22 in our tables, we can see is given by A times 1 minus OR to the N over 1 minus OR. But because OR is greater than 1 here, we're going to say OR to the power of N minus 1 over OR minus 1. We can use either, it still works out the same. But if we sub in, we have 130,350 times 1.014 to the power of 9 minus 1 all over, that should be a 9 there, 1.014 minus 1. So putting into your calculators, and it says again to the nearest 1,000, well, we get 1,241,038. So the nearest 1,000 then would be 1,241,000. Okay, so what you're going to do for me then is going to your books on page 218. I'm going to get you to just do question 19 and 20.